The others may also switch on their cameras. Let us start with it. So what we have seen is that a vector is a quantity which has got magnitude and direction, and it follows vector laws of addition. These laws are triangle law, polygon law, parallelogram law. It follows these laws of addition of vectors. We have seen how to add two vectors using triangle law. We have seen how to add more than two vectors using polygon law. We have seen how to add two vectors using parallelogram law. We have also seen that this graphical approach or these graphical approaches, they have limited utility. They are not convenient in all situations. Therefore, we use an analytical method. We have seen that, how to find out both magnitude and direction. Okay. Component method is something that we are not going to touch upon immediately. And then subtraction of vectors, we have seen. Unit vectors I, j cap, and k cap is what we have seen. Okay, this is what we have done. Today, what I'm going to do is, I'm going to show you, first of all, some applications. Of equations of motion. Equations of motion. Right? And I hope all of you realize that today is the last demo class, right? So I'm just going to assume that you people know equations of motion, and we will take up some very simple examples of, of equations of motion. But after the demo class, if this materializes into the regular classes, then I will not assume that you people already know equations of motion. We'll come from the scratch, derive equations of motion, and then start using. As of now, I'm just relying on the fact that you have covered this actually in 9th class, so you may be remembering this. And the equations that I'm speaking of is V is equal to U plus AT, S is equal to UT plus half AT square, and V square minus U square is equal to 2AC. We will look at some simple situations that can be solved using this. And in the last few minutes, I'll give you various examples, right, where application of vectors actually is very useful in solving the situations. We will not solve all of those in today's class, but basically in 11th class, what are the various places where you come across vectors and how they are useful? I'm going to give you just a brief overview of that. Now, let us write down these equations of motion once again. V is equal to U plus AT, S is equal to UT plus half AT square, and V square minus U square is equal to 2AS. These are the three equations of motion. Write them down as it is. Okay. Now, the first thing that we are going to do from this is average velocity is defined as total displacement by total time. This is how average velocity is defined as. What we want to look at is using any of these equations, we want to write this average velocity only in terms of initial velocity and final velocity. Can this be done? Let us take a look at that. Let us start with this one. Average velocity, the very definition is total displacement by total time. From equation 2, we know that total displacement can be written as UT plus half AT square and divided by total time. So what do we get here? Can anyone tell me what do we get here after this division?
U plus half AT.
Right. U plus half AT, because you take T common outside and then cancel. Right? U plus half AT. Call this as equation 1. What is AT equal to from this? I can bring this U to the other side, right? So AT is equal to V minus U. We know that AT is equal to V minus U. From this equation 1, we get this. Therefore, if you substitute it back there, V average turns out to be U plus AT is B minus U divided by 2. Now, if you take the LCM, 2U plus B minus U whole divided by 2. Therefore, V average is equal to U plus V whole divided by 2. So we are able to find out average velocity in terms of initial velocity and final velocity. Right? Some simple mathematics, a simple rearrangement, and you are able to get something useful using those three equations. Okay. Any doubt in this?
No, sir.
Then copy it down. And while you are writing it down also, if you come across any doubt, feel free to ask. And though I keep using this word, copy it down, don't take it literally. What I actually mean is read this, and if you can really do it yourself. And then look at the screen only if you get stuck up. Otherwise, if you're not getting stuck up, then just continue to do it yourself. Finished writing?
Yes, sir.
Okay. Now, let us look at another application of these equations. I'll delete this and I'll delete this. Using these three equations, can we find out displacement of the body in the nth second of its motion? Let us try to understand, first of all, the meaning of that. Suppose you are moving from a station A to a station B, or a city A to city B. Suppose it takes 10 hours to cover this total distance, some distance. So this will be the first hour, second hour, third hour, fourth, fifth, sixth, seventh, eighth, ninth, 10th, something like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there is one dot extra. Right. Now let us see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. The distances need not be even. They can be uneven, so that's fine. So if someone says, what is the distance traveled in 10 hours? You will count this entire distance and you will say that this is the total distance traveled in 10 hours. If someone says, what is the distance traveled in 10th hour? Then only this will be the distance traveled in the 10th hour. Did you understand the difference between both of them? Okay. Did you understand that? Now, I don't know whether you are keen followers of cricket or not. You need not be keen followers of cricket, even if you know that there is a game of cricket and there are something called as runs, overs, and all that. Then my example will work. If someone says that a team has scored 216 runs in 20 overs and it scored 28 runs in the 20th over. Do you understand the difference between these two statements? 20 overs and 20th over. Likewise, 10 seconds and 10th second, or 5 hours and 5th hour. They both mean two different things. Okay. What equation? See, what this equation gives us is this equation 2. S is equal to ut plus half a d square gives us something like this. It tells us the total distance covered in a time t. It doesn't tell us how much distance was covered in 5th second or 6th second or 10th second, something. Our job now is to calculate the distance traveled in nth second, not in totally n seconds. So what trick will we use here? In order to calculate distance traveled in nth second, just calculate the distance traveled in n seconds, and out of that, subtract the distance traveled in n minus 1 seconds. That's it. Like suppose if you want the runs scored in 20th over, what will you do? You will figure out how many were the runs scored in 20 overs. Out of that, subtract the runs scored up to 19 overs. Then this gap will give you the runs scored in 20. That is how we do that, right? Even in a daily game of cricket, that's how we do it. So if it is that, if that's the case in cricket, why should it not be the case in physics also? So let us go about solving this. Can you do this yourself and check? Try this. I'll be quietly writing this on the screen. So if you don't want to look at the screen, you don't look at the screen, just try to work it out yourself. If you're not able to do it, then refer to this. Okay, so what we have done is we have taken the formula for displacement in n seconds, then taken the formula for displacement in n minus 1 seconds, subtract one from the other, and you'll get the displacement in the nth second, like the first second or the second or the fifth second. That is what we have done. Sidra, what we are doing today is we are just looking at various applications of these equations. Because last 3 classes I was discussing kinematics, which is just like developing the mathematical tool. Today is just the last demo class. So I thought that let us take up a few numericals using the 3 equations that you may have come across in 9th class. Right? Motion chapter. V is equal to U plus AT, S is equal to UT plus half AT square, and V square minus U square is equal to 2S. We are looking at a few applications of that. Out of this is one, what you see on the screen. That is displacement in nth second. Copy this down, and if others finish it too early, then later on take a screenshot if you want to complete it. Otherwise, you can first start writing. Okay, done?
Yes.
Right. Now, let us look at a simple example of how these equations can be used to solve a problem. Okay. And I will clear. Today, we are going to look at this one, simultaneous free fall and a vertical projection. Did I show you this on the first day? Simultaneous free fall and vertical projection?
So you said that you will be explaining this.
Okay, I said that we will be doing this later. Is it? Now, what is the situation here? This is body A, which is dropped with initial velocity 0. This is body B, which is given some initial velocity. You can see the initial velocity of body B, that is 50 meters per second. A and B both are set into motion simultaneously. What we have to figure out is at what height from the table will A cross B, and after how much time will A cross B. First, let us see what is meant by this situation. You can see that the bodies have set themselves into motion. A is gaining speed, B has reached the maximum height, it is coming down, and that is where A crosses B. You can see that with the dotted line, isn't it? This dotted line. Our idea, first of all, is to figure out what is this height from the ground. We have to find out this height from the ground, and we also have to find out the time at which A crossed B. Is the situation clear, first of all? Okay, now let us see how to solve this. It might look complicated, but it is not complicated. At any point during my discussion, if you are not able to understand what I'm doing, just immediately let me. But honestly, remember the instructions. Do not write while I'm explaining this to you. I'll give you enough and more time to write later. Otherwise, you'll get lost out in this. Okay. Now, Let us look at this. For body A, let us use S is equal to UT plus half AT square. Okay, then if I call this distance as H, I'm just writing this here for our convenience. If I write this distance as H and this distance is capital H, this entire distance is capital H, then what is the distance covered by A before it meets B? Up to this point, how much will that distance be? It will be capital H minus small h. I hope that is easy to understand. Okay. Then, if we are writing this equation for body A, then what is the displacement of A by the time it reaches this red dotted line? Isn't it this one, capital H minus small h? So we write capital H minus small h is equal to initial velocity with which A is dropped, that is 0. So 0 plus half of minus G T square. Can anyone tell me why did I take minus G?
Because it's going in the opposite direction of gravitational force. No, wait.
It is moving in the direction of gravitational force, right? Gravity is pulling down and it is also going down. The reason for taking this as minus is, remember what I told you in the sign convention. Anything in the right hand side direction, I cap. Anything in the left hand side direction, minus I cap. Anything in the upward direction, J cap. Anything in the downward direction, minus J cap. I am not writing J cap here, but I am just taking this minus. Minus only indicates that acceleration due to gravity is acting in the downward direction. That is the meaning. Is that clear? Now, in your 9th class, your teachers might have given you a sign convention saying that for any body which is projected vertically up, take G as negative, and for a body which is dropped from a certain height, take G as positive. It looks very cute, right? It looks very cute, nice, as far as it is there in the 9th class. Now the issue comes, suppose I don't throw the body vertically up, I don't release the body, I throw the body horizontally. Then what will you take acceleration due to gravity as? Minus, but I didn't throw it up. Will you take it as plus, but I didn't even throw it down? I just threw it horizontally. Or suppose I throw it like I throw a stone at an angle. Am I throwing it vertically up? No. Am I leaving it vertically down? No. I'm throwing it at an angle. Then what will you take G as? So those kind of sign conventions, they are sometimes a bit cumbersome. They give rise to doubt when you really attack some tough problems like this. Instead of that, another sign convention, and this is not my sign convention, this is the sign convention that is followed in very standard books. Another sign convention is, don't bother about why the body is thrown, where is it thrown, at what angle is it thrown. Anything right hand side, I cap. Anything left hand side, minus I cap. Anything upwards, J cap. Anything downwards, minus J cap. The minus here means that anything in the downward direction should be negative. Any vector quantity should be taken as negative in the downward direction. That is the reason why G has been taken as negative. Okay, agreed? Now, based on that same argument, should I make any more changes to the second equation? Second equation is the displacement of A. Should I make any more changes to the second equation?
Will be positive. Wait for A.
In which direction is A moving?
Downward.
Downward. And how much distance did it cover? Capital H minus small h. But then if I'm saying downward, and when I said downward, I use a minus for G, then when I'm saying downward, I should use a minus here also, because this capital H minus small h is being covered in the downward direction, isn't it? If I just leave it as plus, doesn't it represent upward? Now you see this minus and this minus gets cancelled, and you get the same expression that your teacher has told you in the 9th class. Half G T square. What your teachers tell you is take G in the downward direction as positive, but what they don't tell you is take displacement also positive. then it would be complete argument. So that sign convention is also good, provided it is used completely. When a body is released, you don't just take G as positive. You take displacement also as positive, velocity also as positive. Then it is. But of course, is this understood the way I have used the sign convention? Minus of capital H minus small h because the body is going down. Minus G, of course, because acceleration due to gravity is down. Call this as equation 1. Now let us use the same equation for body B. Which equation are we using? S is equal to ut plus half at square. So if I use it for body B, up to the point where it travels up to this red dotted line, what should I use for displacement? Look at the diagram carefully and tell. Physics is a lot about observation.
Small
h. And is it covering the small h in the upward direction or in the downward direction? Upward. So leave h as positive. I don't have to put a minus sign for that. Right. Its initial velocity u, that is 50 meters per second, was it in the upward direction or in the downward direction? Upward. Therefore, I leave this also as positive ut without putting any negative sign. While it is going upwards, in which direction was acceleration due to gravity? Downwards. Therefore, I have to write half acceleration due to gravity is downward, therefore minus g and t square. Therefore, h is equal to ut.
Wait, why is acceleration due to gravity downward in this situation?
Pardon?
Because they're throwing it upward, right?
Yeah.
Oh, yeah.
We are throwing it up. So the acceleration we are giving it is in the upward direction. But once it leaves our hands and once it is free to travel, is Earth further helping it go up? No, it is pulling it down. And we are worried about what the Earth is doing. It is pulling it down. Fair enough, everyone? Like that, feel free to ask me doubts anytime. I am a very firm believer of the fact that science increases only with discussion. You know what is the situation in Indian schools here? Quite a lot of Indian schools. I'm not saying all the Indian schools, but quite a lot of Indian schools. You are not supposed to ask any doubt in the class. There are teachers who get offended if you ask doubts in the class. You know that? If you ask a doubt to the teacher, many a times the response of the teacher is, what? You question me? But physics doesn't grow like that. Unless you ask questions, you discuss, debate, argue. That is how physics grows. And believe me, honestly, that is how physics grows. That is how your language grows. That is how dance, drama, music, debate, fine arts, liberal arts, law, literature, everything grows only by discussion. So at least as far as my class is concerned, feel free to discuss and ask questions. Okay, I just wanted to tell you that before I proceed. Then, so this is equation 2. In equation 2, you see there is this term called half gt square. But what can half gt square be written as? It can be written as capital H minus small h from equation 1. Right? Equation 1 tells us that half gt square is capital H minus small h. I can use that in equation 2. Therefore, now I'll write small h is equal to ut. This minus is there as it is. Then instead of half gt square, I'm writing capital H minus. Now, if you open up the brackets, small h is equal to ut minus capital H minus of minus plus small h. Small h and small h gets cancelled. So t is equal to h by u. From this, we come to know that the time at which the bodies cross over each other depends both on the height from which the first body is dropped and the velocity with which the second body is put. Getting the mathematical equation is one aspect of it. Understanding the physics behind that equation is another aspect. Right? So from this, we come to know that if you drop the first body from a greater height, will they cross over each other more quickly or will they take more time to cross over each other? They'll take more time to cross over each other because h is there in the numerator. As h increases, t also increases. Whereas if you project the other body from the ground with a higher velocity, the denominator increases. Then what will happen to the time taken? Time taken.
Yes.
Right? We will see all that in the simulation, but first write this down in your notes. You need not draw the table and all that. Just indicate whatever I have indicated here. This one, this one, this, and the equations. All these equations. Rest all content is to be observed from the simulation. You don't write all that. The faster you write, the more we will work with the simulation. We'll see how the bodies cross over each other. What happens when you increase the height? What happens when you decrease the height? We'll see all. So write it very quickly and let me know. After you finish, use that emotion, emote icon. Use that hand raise button or something. Abdul has finished writing. We'll just wait for others also. Nevin is absent today. Rehan joined a bit late. So Nevin is completely absent. Right. Rehan has also finished writing. Good. Right. Sidra has also finished writing. Prithvi Raj finished. Right. Prithvi Raj has also finished it. So remember, T is equal to capital H by U. Okay. So out of all this, whatever equations we don't need, I'll erase that. All this is not required. We can need this equation 1. Again, S is equal to UT plus half it square is not required. And this is what we get by substituting. This equation is okay. All these equations were simplification. So basically, our most important equations were this one. And then using S is equal to UT plus half it square for body B. And using these two equations, getting time T. These were the 3 most important equations. So let us remove all this. Now, what does this equation 3 tell us? That as you increase the height, the time at which A overtakes B also increases. Let us check that. Let us start with a very less height. Because remember, these are simulations. They are not just animations which will just keep playing with a voiceover behind and all that and pretend that you are learning physics. It won't happen that. These are really virtual experiments. Okay. So you can look at velocity of A, you can see velocity of B, and let us fire it. Right. So B is now coming down and there it reaches the ground. Notice this. For 200 H, the time of collision was 4. Let us make a note of that and then reload it and then increase the height. Let us make it 250. Fire. Oh, wait, let us look at the velocity of A also. What has happened to the time of collision now? It has become 5 seconds. So for 250, it has become 5 seconds. Let us increase it further. Let us make it 275 something. Right. Now you see it has become 5.5. 275, 5.5. So isn't it clearly increasing? The same trend that we saw as height increases, the time at which A crosses B also increases. Right? That is how simulations are useful, because can you really do this experiment in real life? Dropping A, dropping B, see where they exactly cross over each other. So in some situations, simulations are very useful. Now let us check the other possibility, that is initial velocity. For that, let us fix A at some distance. Let us say 350. Let us fix A here. And let us start with 50 meters per second. So we are writing this here. H is fixed at 350. We are fixing U, initial velocity, at 50. Now we'll see the time at which the collision takes place. Right. So you see, collision takes place at 7 seconds. Now what we will do is, we will not increase the height now. Height is fixed. Let us increase the initial velocity. Earlier it was 50. Now let us make it 60. 5. You see, what is the time now? 5.83. When it is thrown at 60 meters per second, 5.83. So as expected, as velocity is increasing in the denominator, the time is decreasing because it is on the left hand side. Okay. Let us look at just one more case. Let us really fire it up. 80, 90, 100. 100 is the upper limit that I have given. Now let us fire. You see, B has already gone out of screen, but don't worry, it will come down. But look at the time, 3.5 seconds. So when you fire it at 100 meters per second, it is going to cross here at 3.5 seconds. Now it is taking its own speed time to come. So this proves that as the initial velocity of projection is increased, the time within which the collision takes place obviously decreases. Now comes a very interesting thing. Let me just decrease the velocity a little. Earlier it was 50, right? We had started with 50. Let us go up to 30. What do you think will happen?
Time will increase.
Time will increase. A will take more time to cross over B. अब देखते हैं, बहुत मजा आएगा. Where is that red dotted line? It is missing. Why is it missing?
It's on the ground.
Because A could not cross B before B hit the ground. And our condition was, when will A cross B? Before either A or B should touch the ground. The crossing over should happen before that. Could A do that? Let us reload and see. Let us remove all these velocity spaces. Let us just look at this. You see, this is where B reaches the ground and A is still catching. So now let us increase the velocity a little bit. Let us make it 40. Pause. What do you think will happen? Will A catch up with B? No one wants to take any guess. Everyone is thinking that, okay, it is A and B's personal issue. Why should we interfere between them? So let us see. If they meet, they meet. If they don't meet, they don't meet. Right? Chalo dekh. B is coming down. Gone. There is no red dot. It means A could not catch up with B. Let us increase this by just about 2 meters. Reload. B has reached the maximum height. B is coming down and A is catching up really fast, just at the ground. Doesn't this prove that there should be some minimum velocity with which you should project B? If that minimum velocity is not given, then A will not be able to catch up with B before B reaches the ground. You know what is the next interesting thing? To find out what that minimum velocity is. And how do we do that? For that, let us put T back in this equation and see what do we get. Small h is equal to U into T will be h by U minus half G. T square will be h by U whole square. So when you simplify this, you'll get small h is equal to capital H minus G h square by 2U square. Is it clear up to this equation? Equation 4. Now, when you want the collision to take place either above the ground or on the ground, what does it tell you about h? It means small h should be either greater than or equal to 0. Isn't that the condition that we are looking for? If small h is greater than 0, then A will cross over B above the table. And if small h is equal to 0, A will cross over B just before hitting the table, like the diagram that you see. Are you able to understand that? This language of mathematics. Right. So now, since h has to be greater than or equal to 0, what is h equal to? This one. So I can write capital H minus G h square by 2U square should be greater than or equal to 0. So, yeah.
So, like if h is equal to 0, then that means that the balls will collide just before hitting the table.
Hitting the table.
So
Just
after hitting the table, it will be h's value will be a negative number since it's a displacement.
After hitting the table, you know what that condition means? That condition means that you project this body, you leave this body, and then remove the table. If you remove the table, then the bodies will continue to travel down. Then A will catch up with B sometime later. But are we allowing that condition to happen now? No. So we are not looking at h value being less than 0. Less than 0 means below the table. Equal to 0 on the table. Greater than 0 above the table. Okay. So now you have capital H greater than or equal to G h square by 2U square. This and this gets cancelled. Therefore, 2U square should be greater than or equal to GH. So U square should be greater than or equal to GH by 2. Therefore, the initial velocity with which you throw the body B should be greater than root of GH by 2. If it doesn't satisfy this condition, then B will reach the table before A can catch up with it. Right? If it satisfies this condition, again same thing, greater than A. If it satisfies this condition, then yes, A will catch up with B before B reaches the table. Are you able to understand that? Right. Don't write this now. We'll be doing more of this stuff later on once the regular classes start. But then just don't do this. This is just an example. What happened to my pen? Yeah. This is just an example to tell you that while using vectors, we must be careful with that plus minus sign, because we were able to solve all this only because we took capital H minus small h as negative, minus G also negative because that was down. Whereas for the second body, small h was positive. It was possible only because of all that. Right? Now, similarly, you see simultaneous free falls from two different cases. A is dropped and B starts falling just when A crosses B. Now, you know how many kinds of questions can be asked for this. What is the velocity of B by the time A reaches the ground? What is the velocity of A by the time it crosses over B? What is the relative velocity of A with respect to B? Like that, there are many possibilities. Each of the simulation, we can spend almost half an hour on that by discussing various cases. I'm not doing that now. I'm just telling you how it can be done. Then your vectors can be useful in this case also. This is one body A, which is thrown horizontally like this. And this is another body B, which is just allowed to fall down. Which body do you think will reach the ground first? If I allow them to move like this, right? I deliberately reset it quickly. Which body do you think will reach the ground first, if at all? Body A or
B.
body B will reach the ground because it is dropped, it is covering a distance. And Sidra believes that A will reach the ground because you are giving it some velocity. Right? Both of them reach the ground simultaneously. The reason is because, see, this is the velocity that you gave to body A. While it is moving, in my simulations, there is another facility. You can use this plus symbol. Click here, it will move step by step. See, at any point you see, body B is covering the same vertical distance as body A. You see, body B is covering the same vertical distance as body A. Question is why? Because this velocity that was given to A, it was given only in the horizontal direction. It is because of this velocity that A is not traveling vertically, it is moving forward. It is moving forward because of that velocity. But can it come down because of the velocity given in the horizontal direction? It cannot. Therefore, in the vertical direction, velocity of A is same as velocity of B. Therefore, the vertical motion is same, horizontal motion is different. You can check that for any other velocity also. You can increase the height and you can really fire up A. You can see that the velocity vector is increasing. Now you see the Y component of velocity, total velocity, and this. Let us leave out total velocity and play. Compare the vertical velocity of A and vertical velocity of B. Aren't they same? Yes. And the height traveled by A and height traveled by B, aren't they same? Therefore, the time taken by A is same as time taken for B. But B is lazy, it is just coming down. A, while coming down, it is also moving horizontally. The reason is because it was given some velocity. This is where a vector's resolution into I cap, J cap, all that I was hinting about in the last couple of days, that will be useful in solving these kind of problems. Then let me tell you another instance where it is used. Boat river problem I have already shown you. This one, oscillations of a loaded spring. Suppose a body is attached to a spring and you set it into oscillations. You can see that the spring is oscillating. Now, if you look at the displacement of the body, this brown body, you see when this is going down, the arrow is going down. When it is going up, the arrow is going. So isn't this continuously changing direction? So if this is changing direction, should you not keep a track of where the body is along with the plus and minus sign? That is where your vectors become useful. Now you see the velocity of the body, you see the acceleration of the body. Do they even seem to be matching with each other? One is going up, one is going down. And later on, of course, this will come only 5-6 months later. You don't have to worry about this. But still, all these things are. Another classic case where your vectors will be important. And after that, we'll close. I'll just show you this in LB. Movable wedge, movable inclined table system. Okay, this is the classic case where there is one body kept on a table, other body that is suspended from it, and the moment you release both of them, how will they move? This is how the bodies move. And in this simulation, what you can do is you can decrease the angle of the table, or you can increase the angle of table. You can increase the mass of A, you can decrease the mass of B, then you can play it, and then you can see how the bodies move. We will be solving all this, no doubt, but pay attention to this one. Isn't this a vector quantity? What quantity is it? You can worry about that later on. But the very fact that it is given by an arrow means it's a vector quantity. Here it is a vector quantity. This is a vector quantity. Upward force is a vector quantity. Downward force is a vector quantity. That is why I was telling you vector quantities are very important. Clear up to now? Now, those who are interested later on after the class is over, you can play around with all these simulations, right? The gray ones, they are yet to be updated. All this dark, light brownish kind of ones. The one with this yellow or purple, blue or purple color, they are already up. You can play around with that. Totally, I'm working on almost like 260 simulations, out of which around 50 are already there here. And during this academic year, I'll see how many can be completed. I'll do that because in between my classes and all that, whenever I get free time, I sit for this. That's either this or music. These are my two hobbies. So I keep working on it. You also keep working on it. Keep, thinking about science, trying to do something with science. Right? So that's all for today. I had a very nice interaction with you people over the last 4 days, and we'll see how it goes. Right? Bye, everyone.
Thank you, sir.
So should we leave
Thank
the
you, sir.
contact number in the chat box?
Pardon?
Contact number.
Our Mohit sir will give you. Mohit sir, or what is his name? Oh, wait. He was there in this group. Yeah, Math IIT online host. I think he'll be able to give. Right? Yeah, fine. Thank you, everyone. See you soon. Bye.